very much for the opportunity to speak. Wasn't real sure we were going to make it after all our adventures at the airport, but anyway, here we are. This is the second time we've been to South Africa. We were here in 1999 when we visited Potchefstroom and Cape Town. Yeah. So anyway, I would like to talk about the Orlicz-Pettis theorem, which is one of the early results in functional analysis. And let me just explain a little bit about what the statement is. So we start off with a norm space, the dual and its weak topology. And then a series in a topological vector space is said to be subseries convergent if every subseries converges. So just exactly what you would expect. And then the theorem is that if you have a series and it's subseries convergent in a weak topology, then it's actually subseries convergent in the norm topology, so a much stronger topology. And that was done originally by Orlicz, and it's actually in Bonnach's book. But there wasn't a proof available for the American mathematicians, so Pettis was working on what is now called the Pettis integral. And so he reproved the theorem in 1938. So, and that's the reason it's referred to as the Orlicz-Pettis theorem. That's quite remarkable. So you have a series, subseries convergent in a weak topology, and all at once it gets to be subseries convergent in a stronger one. And for example, that's remarkable because if you have a norm space, the weak topology is always strictly weaker than the norm. So somehow the subseries convergence makes this possible. So what I want to do is sort of rephrase what subseries convergence means. And show you one way at least to try to extend this. Now, applications. Well, the most applications you'll find of this theorem are in measure theory and integration. And so here is sort of one of the places. Suppose you have a sigma algebra, and you have a finitely additive set function. It's got values in a norm space or a Banach space, and you want to show it's countably additive. Well, you can use this theorem. All you have to do, instead of working with the norm, you can simply work with these scalar measures. You just compose an element of a dual, the set function you have, and if it's countably additive for all of the x primes, then it's countably additive in norm. And that's actually what Pettis used the thing for. He showed that the integral he defined is countably additive, and he used exactly that theorem to do it. I won't tell you what the Pettis integral is, but I'd be willing to after this talk if you're interested. And the theorem was extended to, this is one of our abbreviations, locally convex spaces by MacArthur and Grothendieck, and it's been generalized in more directions you could ever imagine. Now, what I want to do is rephrase the notion of subseries convergence so we can look at another version of this theorem. So, a series is subseries convergent. The chi-sigma here is the characteristic function of sigma. So it's 1 on sigma and 0 all. So all you're doing here is just picking out the subseries by using the characteristic function. Now, let's let M0 be the span of all of these characteristic functions. So that's just a sequence space that where the sequences all have finite range because it's a span of characteristic functions after all. And so this series is subseries convergent if and only if this series summation Tj xj converges every Tj in M0. So So let's rephrase the theorem. So here's the Orlicz-Pettis theorem. If this series that I have here, so this is the series we're going to be looking at. So here are the elements in 0. So if this series converges for every sequence Tj and M0, and subseries convergent, then it's norm convergent. So why would that be useful? Well, think about this now. Right now, we're considering to be in a sequence space M0. But what if we try replacing this sequence here by another sequence? Can you obtain an Orlicz-Pettis theorem in that setting? So anyway, that's the remark here on the whatever you call that, the projection. Can you replace M0 by other sequences? Well, that's a reasonable question. So let's just consider that for a moment. So let's start off with an arbitrary sequence, a scalar sequence, a scalar vector space of sequences. And for a reason you'll see later, we require it containing C00, which is all of the sequences which are eventually 0. There are two reasons for that. One, you want to have enough elements in your sequence space to make good sense. And then there's another reason which I'll explain later. So then we just say that a series values an X. Am I messing that up? I'm sorry. I told you I wasn't used to technology. So we say that a series is lambda multiplier convergent. If this series here converges for every sequence in lambda instead of in 0. So the question is, can you get an Orlicz-Pettis theorem when you just have when you replace M0 by another sequence space? Well, that would be a lot to hope for. And in fact, you can't do that in general. So see if I can not mess this up when I change pages. Okay. So let me just give you a very simple example here. So C sub C. All of the sequences that are eventually a constant. So just imagine replacing these elements here by a sequence space where the terms are eventually constant. Well, that just means the original series would converge, because after a while you just have a constant here which you can factor out. So suppose I have a series then that can sequence, let's say, converges weakly but not in norm. Well, if I just put in a telescoping series, then there's no way, a weakly CC convergent series would ever be norm convergent. So the moral of the story is that you can't get an Orlicz-Pettis theorem without some conditions on lambda. So you have to have something there. So unfortunately, you have to bear with me a while. I need to introduce some terms and some machinery here to explain how one can obtain an Orlicz-Pettis theorem for these multiplier convergent series. So the first part is topology. Okay, so we have a dual pair of vector space. This is the bilinear pairing between them. And so we have weak topologies. And so we start off, I always think of these things like this. Here's X, here's X prime, stacked like that. So I take a family up here that consists of sigma x prime x bounded sets. Okay. Now I take one of the elements out of there, and I can define a semi-norm down here now. So x is down here. So for each element, each weakly bounded I have here, I just compute the sup over at x. I just compute the sup over all of guys in A, and then you look at the house of A. House of A is the locally convex topology. Generated by these pieces of A's. Here's what you call it. So if you're looking at a net or a sequence down here, it converges to 0 if and only if it converges uniformly on each one of the elements here. That's called the polar topology. The reason for the word polar I won't try to explain right now. Anyway, there's a very good reason for that. Okay, so that's one thing we need. So what are examples? Well, I'm just going to list the three most important. So one is the strong topology, and that's where you use all of the weak bounded sets up here. The weak topology is where you use the finite sets. And then there's one in between. It's called the Mackey topology, and there you're using convex, weak, compact things. Now, if you're not familiar with all those things, think of it this way. Those are important topologies. Any metrizable space always has the Mackey topology. And any Banach space always has the strong topology. Of course, there are lots of others in between. So these are very commonly encountered. Yeah. Okay, and then we have another topological thing. That's, so again, we have this dual pair, any dual pair. So we have a topology that I'm calling it W now. It has to be defined for all dual pairs. So the strong and the weak and the Mackey would be examples of those. Okay, and then the definition is, this is due to Wolanski and that W there. You say that W is a Hellinger-Topos topology. Anytime you have a linear mapping from one space into another that's weak continuous, it's continuous with respect to the two W topology. Now the good news is that if you write down a polar topology, the probability is 1 is the polar topology. And I've never really figured out why Wolanski called it a Hellinger-Topos topology, but anyway, that's his terminology. So we'll stick with it. So again, the examples are the strong and the Mackey. Mess that one up. Okay, we need one other notion now. So if you have a vector space of sequences, it has what's called a beta group. And that's just simply all of the sequences such that the series summation Tj, Sj, convergence for all of the S's in lambda. So when you have this now, you have a very natural, so this is a dual pair, and that's one of the reasons that you require this space to contain C00, 0. So you have the separation property for dual pairs. So very often the beta dual and the topological dual are the same, but not necessarily. So that's one thing. So we have a dual pair. Here is the pairing. You have a T up here and an S down here. That's the pairing between. Okay. And one other thing we need is the notion of an AK space. So we assume now that lambda has a locally convex topology. An AK space is you take a T out of lambda. It has an expansion. The EJs now are the canonical vectors. There's 1 in the J place and 0 in all the others. So it looks like this. This is in the J. So they're just the canonical vectors. So if you can always expand the thing out like this where the convergence is in lambda. So examples. Well, the examples that I've written down here, C0. C0 now is the space of all sequences. And then everyone knows what the little LPs are. So those are AK spaces. L infinity and M0 with the supernorms are not AK spaces. So we have a theorem now that tells us when we have an Orlicz-Pettis theorem for multiplier convergent series, and it goes like this. Okay, so I have a Hellinger-Toeplitz topology. The following are equivalent. Lambda with the Hellinger-Toeplitz topology is an AK space. And the other one is for every dual pair series next, which is lambda multiplier convergent in the weak topology, is lambda multiplier convergent in the Hellinger-Toeplitz topology. So what 2 is just exactly the conclusion of the Orlicz-Pettis theorem. Weak convergence, we get better. So what good is this? Well, it gives you a way to test to see if you have a Hellinger-Toeplitz topology. These are necessary and sufficient. So if I have a sequence space and I want to test it to see if I have an Orlicz-Pettis theorem, this gives me a way to do it. I just check, see if the scalar sequence space is an AK space under the Hellinger-Toeplitz topology. The proof is very simple. It's very straightforward. If we have some time, we can talk about that. So, what are examples? Well, C0 and the LPs. Because again, you notice up here there are AK spaces. Now, we want to apply this to subseries convergence. And that's where you use M0. Well, M0 with the supernorm. And there's no way that's an AK space. You've got a sequence there that's constant. Sorry, it only has a finite number of terms, so there's no way you're going to get convergence in the supernorm. So one could ask reasonably, well, how does this theorem help you with subseries conversion? Well, this M0 is not an AK space under the supernorm. There are topologies under which it is an AK. I'll try to write one down for you. So anyway, that's how M0 and subseries convergence gets into the picture. So, what can we do to find examples, reasonable examples of species that for which the Orlicz-Pettis theorem holds? Well, luckily there's a very nice algebraic condition that guarantees that, and it's one that's easy to check, which is always useful. So again, if you'll bear with me, I'll try to explain what the conditions are. Okay, so if I have a subset of the positive integer, and I have a sequence, scalar sequence, then I write chi sigma t. That's just a coordinate product of this sequence with that sequence. Okay? So you just multiply out the coordinate. Okay. Then what about an interval then? Positive integer. Well, you get no big prize for guessing what that is. Just look at all of the integers that sit between. Two integers. So you had to, here you're looking at all of them, you're just looking at some subset that looks like that. Okay, so it's an interval except you're just using integer entries. Okay, and then if you have a sequence of these things, you say it's increasing. Again, you get no big prize for guessing what that means. Here's a bunch of them that go like this. So what do you want? You want the max of this one to be less than the min of that one. So they parade along. And then we have a definition. So lambda has the weak dividing home property. If for every increasing sequence of interval diagonal in T belongs to lambda, there is a subsequence MJ such that this series falls back into lambda. This is the coordinate sum. Let's see if I can draw a picture. Okay, so let's forget about the subsequence part. Let's suppose we have a sequence here. Okay. So what do? So I've got the sequence, then I've got an increasing sequence of intervals, so they go along like this. So what am I doing when I'm looking at this series? If I'm over one of the intervals, I'm taking all the entries over that interval. And where I'm not over an interval, I'm just putting zeros in. So that sequence has to fall back into lambda. So what would be some simple-minded examples? Well, C0. That's all sequences that go to 0. Right? So if I have a sequence up here that went to 0, and I section it off like that, it's still going to go to 0, right? Because I'm filling in zeros that the sequence lived before. Another good example. What about the LD? Well, let's do L infinity. So I start off with a bounded sequence, and I section it like it's still going to be bounded. So this is an example of something with a weak dividing property. What about our friend M0? That's just all of the sequences have finite range. Well, if I run along and I section again like that, it's still going to have finite range. So all of these guys have a weak dividing up problem. And then I didn't write it down. Well, I did write it down, and then I erased it. These likewise. And again, that's easy to see. Because if I had an LP sequence and I go along the section, it's still going to be. So there's a whole myriad of these things. Well, so what good are they? Well, so they're good in this sense. If you take lambda, it has the weak dividing hump property. And you look at it with this Mackey topology. Okay, so here we have lambda and lambda beta. So this is just a Mackey topology. This thing always is AK. So by the theorem, then anytime you have a sequence that has the weak dividing up property, you've got an Orlicz Pettis. So here are these examples. So those are sequence spaces for which the Orlicz Pettis theorem holds. Yeah. There's actually a generalization of that. One of my PhD students made a very nice observation. He weakened this condition. He called it a weak signed weak dividing up property. Every sequence, same thing here. Over here, we have a sequence of signs. Say S1J, such that when you put signs are just plus or minus 1. When you put signs in there, you have the same condition holding. So, well, that's something nice to define, but are there any examples? And so, what he showed was that BS is the bounded series. This space has the signed weak gliding up property and not the weak gliding up property. So there are examples, and again, this theorem. Well, again, that expands the list of sequence spaces for which the Orlicz Pettis. Now, one thing, so that's sort of the good news. Now, what about the bad news? Well, one would like to have an Orlicz Pettis theorem for the strong topology. So think about a bottom space. Well, here, let's look at this example. Let's look at L1. Let's see, and L1. So let's look at that dual. Let's look at the series down here. Summation EJ. Remember now, EJ is the sequence that's got a 1 in the J spot and 0 everywhere. Well, this series is sub-series convergent in this topology. Because, you know, anytime I take this sequence and I hit it with an L1 thing, it's certainly going to converge. But what about the norm? Because the L-infinity norm of the Jth term is 1, so it couldn't possibly converge. So, if you want an Orlicz Pettis theorem for the strong topology, you have to have some really stringent conditions on the multiplier. Now, there are conditions that guarantee that. Yeah, I've written one down here. And it's a fairly straightforward statement. Unfortunately, it doesn't apply to a lot of sequence spaces that you know. But anyway, essentially what it boils down to is you have to have, well, you don't have to have this, but anyway, this is barrel. I don't know how much people here know locally convex space theory. Barrel is essentially where the uniform boundary goes. So if you have two spaces, E, say you have a locally convex space. What is the guy barrel? When you look up in the dual and weak bounded things up here are strongly bounded. So that's barreled, and then we see the AK before. Okay. So if you have a lambda, then you have a Orlicz Pettis theorem for the strong topology. And what about examples? Well, about the best you're going to do is you look at LP. These are bottom spaces, so they're certainly barreled. And they're all AK. Notice I don't include infinity there. So they're all AK. C0 would be another one. So now there are conditions on the multiplier space that also guarantee Orlicz Pettis theorem for quality, but they're complicated. I don't want to harass you by writing one of them down. But anyway, there are such. So I've written one down here. But it's fairly complicated and it's not that easy to check. But they exist. So I think at this point I'll probably pause and ask if they have a question. I can try to answer. I don't know exactly what people's background is, so I don't know exactly what I should be saying. So are there questions?
I'm interested in the beta dual. The beta dual.
The beta dual?
Yes. The pair. I'm fascinated by their properties. Presumably, one implies the other, and they have mutually similar convergence properties. Or if one, am I correct to say that if one member of the pair converges, it forces convergence in the other member?
Beta dual now. So I have a sequence-based lambda. This beta dual is just all of the sequences. So it's all of the sequences where when you form this series here, it converges for every Sj belonging to lambda. So see, I take a sequence out down here, S. And now, if I want a sequence, if I want to look at a sequence up here, so this sequence belongs to the beta dual. Whatever you this is, think of this as a formal dot product, right? I've got two sequences, and I just form a dot product by multiplying coordinates and adding them up. So I require that this converges for every sequence down here. Okay. So very often the topological dual and the beta dual are the same thing, but not always. So for example, if you have C0 with the supernorm, okay, then the beta dual is L1, and that's also the topological dual. But for these spaces, well, let's try L infinity with the supernorm again. Okay, so the beta dual here is L1. See, I would be asking what series, what sequences up here have the property that when I multiply them by a bounded sequence of convergence. So that would be L1. Okay. But if you want to look at the topological dual, I don't know if you're familiar with that. It's humongous. It's what's called VA. VA is a set of all bounded, finitely additive set functions on the integers. So that's a huge thing, right? So M0 is the same thing. Dual is L1. The topological dual is VA. So sometimes they're very, very different. That answers your question.
Oh, no, you
Actually, I don't know. Again, I don't know people's background, but there's a book, I think it's called Sequence Spaces by Campton and Gupta. It's a whole huge list of sequence spaces with the beta duals and the topological duals. Let's do that. I don't know if you have that in your library or not. If you're like our library, you're part of 5 books.
Yeah, and the diagram you have there at the bottom where you have those closed intervals,
Yeah.
and you were talking about linking them up so that they become one. Is that what you mean?
Well, no, you have a sequence, you start off with a sequence, which I tried to indicate up here, okay? So it's fixed. So I look at the intervals as I go along, right? So I form a new sequence. Over the interval, I keep the enters in the original one. If I'm not in an interval, I put in zeros. Okay, so I would go along. Every place I see an interval, I leave it alone. When I don't see an interval, I put in zeros. Okay. So well, okay, so what's an example of a let's look at an example of a space that doesn't have a property. C. C is a space of all convergent sequences, right? Now, suppose I took a convergent sequence. So say the constant sequence 1, that's a good example. And I take a sequence of intervals and I section it. So I'm taking ones here, and I'm putting zeros in there. There's no way that converges, right? So that's an example of a space that doesn't have writing our property. And you can, like, space of convergent series, right? If I had a convergent series and I ran along and I put zeros in places, it may not converge. Right? Think about the harmonic series, right? So there are lots of spaces that don't have that property, but it's a nice property as far as the Orlicz Pettis series is concerned.